I hope you see the first slide, the title slide.
Yep.
Great. Okay, so I'm actually going to be this deck is for 2 sessions, both this one and the next one. The first session is Introduction to Practical Knowledge Representation and Logic, and the second is State-of-the-Art Practical Reasoning and Meta Logic. So I just want to give some acknowledgement and thanks that there are several collaborators that contributed to this slide deck and the contents of the presentation, including Michael Kiefer, Alex Gray, Janine Bloomfield, Teresa Swift, and Paul Fodor. Thanks also to Kyle Irwin for input. And a longer version of this tutorial material will be available on the web at my personal website and also Coherent Knowledge website, which is where I'm chief scientist, although I'm moving soon. I'm planning to move soon to DARPA as a program manager in its Defense Sciences office. So there probably will be still a few imperfect summarizations or correspondences due to the fact that I had limited time to subset this slide set for a 2-hour version from a longer 6-hour version, which was first presented at a seminar series in March. Okay, so let's get going on the first session. One way to think about AI is that in terms of the relationship of knowledge representation and reasoning, i.e. KRR, and machine learning, i.e. ML, is that it takes 2 legs to walk. What is logical knowledge representation? So I'm going to give a formal definition. Often people talk about this fairly informally, especially in the machine learning community, in a way that is not really quite right when talking about representation. So it has very specific meaning in the logical end of AI. We talk about a given logical system having both a formal language and so-called semantics. The formal language, actually there's 2 parts of it, one for assertions and one for conclusions. And unlike in classical mathematical logic, those 2 formal languages of what are permitted syntactic expressions may be different for the conclusions than they are for the assertions. So for example, in the declarative logic programs, KR, the RULOG KR, which is an extended form of LP, the logic programs, and also, for example, in BaseNets, there are non-overlaps between the assertions and the conclusions. So now let's talk about semantics. This is usually defined in terms of an entailment relation, where a set of assertions entails a conclusion set. And here we're going to assume there's exactly one conclusion set, i.e. what is the set of stuff that you believe skeptically, if you know what that means. Typically, entailment is defined formally in terms of models. A model is a truth assignment on the language of conclusions that meets criteria based on the assertions A. So, for example, in classical first-order logic, in LP, and in RULOG. Reasoning implements the semantics, for example, to answer queries. And so we talk about a software system doing knowledge representation and reasoning. I've underlined the second R. Typically, these systems are sound, but often incomplete. We'll discuss the formal definition of soundness and completeness later. But intuitively, you can think of soundness as when they conclude something, they do so correctly. But incomplete means there may be conclusions that are sanctioned but not reached. Now, let's think about the relationship of induction and deduction. A very important one is that induction in machine learning requires deduction. So let's take a very high altitude view of ML. The way most ML induction or training works today is that an algorithm iteratively searches for models, typically with some randomness, i.e. stochasticity, stopping when the search when returns diminish, then analyze the accuracy of predictions that are made on focal examples, typically via penalties or distance penalties for error, often on subsamples. And this involves a heavy amount of deduction going on in the inner loop of the machine learning in order to compute what those predictions are. Another key step is to analyze simplicity of the model, typically with a penalty for more parameters or some other measure of complexity of the model. And then analyze the goodness of agreement with other previous knowledge. Say when you're doing incremental learning, you've got maybe you're doing fine tuning, or you've just received a new batch of examples data, labeled or unlabeled. And this also, analyzing the goodness of agreement, involves a heavy amount of inner loop deduction to compare the previous knowledge and its predictions or other characteristics with the latest iterate. And then the analysis is fed back to develop directions for the next iteration, typically via differential gradients, for example, in neural nets, but also in a lot of Bayesian type of machine learning. In neural nets, i.e. NN, the deductive KR has logical expressiveness that is quite low and is oriented toward addition, multiplication, essentially arithmetic type operations. However, some other ML approaches have KR that is significantly more expressive in the form of the knowledge or the form of the elements of the model that are being composed together to create the overall model. In general, there's a dialectic between KR and ML. They're the two most core reusable areas of AI for many decades. KR is intellectually as rich, deep, and broad as ML. All along, there's been a dream in AI, which is to bring KR and ML in a way that combines them much more tightly than people have figured out how to do effectively in the past. Every decade or so, the pendulum swings between KR and ML as practical foci. So in the 80s, there were expert systems. Then in the 90s, basic machine learning rose. Then in the 2000s, semantic web, which is basically KR again. Then there was Bayesian machine learning and deep neural nets. And neural nets prediction can actually be viewed as deduction in this low expressiveness KR. So here's an overview of what I'll be covering in the rest of this session and the next session. What is KR? What's practical? The landscape of it in the industry, its centrality, the centrality of the logic programs, LP's KR approach, and various concepts around KR, such as syntax, semantics, etc., that I've listed here. Some desiderata and foci generally for KR for the purposes of neurosymbolic, or what's sometimes called learning and reasoning, or third wave AI. And we can think of classical logic, which you learned in school and is used in mathematics, in terms of various restrictions or features of both the language and its semantics, but also of proof procedures, and then some significant restrictions on it, which help deal with its computational complexity, which is fairly high, and some of its drawbacks, an outstanding one of which is brittleness, especially in the face of conflict, but also in some other ways. The normal logic programs, KR, has some significant differences from classical. Some of it involves restrictions. It's based on a semantics that involves, or a proof procedure, also constructive semantics, which can be thought of as an idealized proof procedure involving at least fixed point, but also introduces a form of negation that's different from classical logic, and also has an important relationship to practical structured information management in the form of relational databases, programming languages in the form of Prolog, and also doing what's called orchestration in services composition. And we'll talk about some other aspects. The extended logic program group of KRRs has a number of different features that extend basic LP. And a key way that these are often defined and semantics is analyzed and proof procedures are developed is in terms of transformations. There are a number of kinds of uses that are associated with it. And one fairly good-sized bundle of such extension features is called RULOG. One of the kind of aspects that's really important to understand about these practical KRs in the ELP group is that they have quite a bit of expressiveness around meta information or meta logic. And remember that the web, its big innovation compared to the predecessors in information management was fine-grained mixing of metadata with data. So here we can think in terms of meta knowledge being mixed with other kinds of non-meta or base type knowledge. An important aspect is so-called defeasibility, namely that there's argumentation, rules may have exceptions, or other statements that are complex may have exceptions. And many broad realms have this character. And so if you're going to do KRR or learning in those realms, you should have a KRR that is equipped with defeasibility. Then there are various other more hard to categorize types of things. A key thing, though, overall in the meta is higher order and also uncertainty, including probabilistic. Another key attribute is explainability, and the ELP group has a strength in terms of natural deduction, being the style of its proof procedures and its semantics being conducive to that, and that really helps people who are not logic experts understand quickly how conclusions were reached and then support the debugging as well as the process of reaching trust in systems engineering generally. We'll discuss along the way a number of different tools that are state-of-the-art and open source, and wind up with revisiting a bit some desiderata around the scalability and other socio-technical characteristics of ELP, which are really significant differences and advantages compared to classical logic. So practical logic differs from classical logic in that the goal is to support IT, information technology, rather than mathematics. So for example, databases, knowledge graphs, rules a la business rules or programming languages. This LPKR is central to it, and essentially it's an extension of the logic of databases. In fact, declarative logic programs were originally developed as a concept and studied in order to unify the abstraction of relational databases with Prolog type programming language. Now, a key requirement when doing practical logic is to be scalable, both computationally and also socio-technically. In other words, when you have systems that are combined of a combination of humans and automated processes. We want to be reliable, explainable, flexibly expressive, including in the meta aspects, be compositional, both within KR and also between logic and other kinds of systems. For example, hooking them up to machine learning systems or natural language processing. And be friendly to both structured information and natural language, as well as to software engineering and other kinds of systems and programming. Another key requirement is to be robust in the face of human errors and miscommunications. And this is a key to being scalable socially or socio-technically. And one of the implications of this is that it's important for the KR to be humble in a certain sense, to avoid general proof by contradiction, which is premised on that any inconsistency is intended, essentially. And whereas practical systems and engineering efforts by humans, there usually are some errors that are unintended at any given point. Another is to avoid general reasoning by cases. I'll explain what that is in a moment, but which is at the heart of the intractability of even the propositional case of classical logic. So consider the following set of three assertions. If A, then C. If B, then C. And we know that either A or B So in reasoning by cases, we can conclude C, and this is at the heart of 3SAT, which is the original NP-hard problem. It's the unrestricted ability to apply reasoning by cases kinds of patterns of reasoning that produce that intractability. What does semantic mean? It has a very specific meaning in logic and KR, which is somewhat distinct from the meaning that it is employed in natural language processing. Basically means based on logic, and this could apply to rules or technology or to the web. So we talk about semantic text, semantic web. And it has advantages for communications across systems and organizational boundaries. Meaning is essentially a shared notion of what is versus is not inferable, and it abstracts away from implementation. Relational database was essentially the first successful semantic tech, and as I mentioned, the theory of LP was invented to formalize it and unify it with the pure subset of Prolog. So when we think about desiderata for KRR, especially for kind of in itself, but also for purposes of being neurosymbolic or generally learning and reasoning, there are some important foci here. Of course, it has to be suitable for a set of applications. So considering decisions, knowledge sources, and the kinds of desired analytics. Expressiveness is essentially flexibility about what and how you can state, edit, and infer knowledge. Syntax does matter sociotechnically. It's not the case that expressiveness is essentially the same as irreducibility or reducibility in a formal or mathematical sense. It's about what one can state and edit and infer in a way that's convenient, especially concise, as well as clear. And there are a number of expressive or extension features that are highly desirable for various kinds of knowledge and application usages. The creativity in the field of KRR is to combine suitable restrictions and extensions in such a way that you're able to get a good combination of characteristics overall, including not only the expressiveness, but some of the other considerations that I'm about to describe. So a second important thing is computational scalability, preferably polynomial time practical tractability. Sociotechnically, scalability has a number of different aspects. I'm not going to try to define it right here. We don't really have time. But one thing that bears on it, for example, is compositionality, including modularity and reusability, ease of updating and modifying in the knowledge. And LP and extensions of LP, including RULOG, have a very fine-grained kind of compositionality. A locale there is a set of rules that mentions a given logical literal. A literal, we're going to see how that is defined syntactically and semantically later. And then one can walk syntax dependencies in terms of those locales, structured by those locales, and proof procedures, including ones that do incremental inferencing after you receive some new assertions to union with your previous assertions, exploit this modularity around locales and this ability to walk the syntax dependencies. So for example, during subgoaling, during inferencing procedures. As a software component in overall systems engineering, of course, compositionality is important, including to do orchestration via querying out to other components to get information dynamically or doing data transfer of other kinds, say batch, inbound as well as outbound to a logical reasoning component or knowledge base. And to have convenient interfaces for typical enterprise data environments is quite important. You want them available and you want them to fit in well with the overall semantics of your knowledge representation and reasoning. And leverage standards for that, including for interoperability and certain kinds of optimizations. Explainability is another key thing to being able to achieve trust in systems and get to the point where they can be deployed and essentially to socio-technical scalability as well, including interpretability and transparency, etc. It's important to have comprehensibility by non-programmers and people who are not AI experts. It's crucial to get to high accuracy by doing debugging and thereby get to trust. Robustness in the face of contradiction type conflict is important also because that tends to arise from several different causes, including human errors, uh, underspecified shared context, and some other things. Completeness is often required for even soundness, for example, in defeasibility. Now, why LP with respect to these desiderata? Why is it a good match? Well, in terms of scalability, it's tractable for very broad cases. We can think of this in terms of the V's in big data. Two of them are volume and velocity. Its tractability is far superior to classical logic for kind of comparable cases, and we'll see what that looks like a bit later. In terms of social scalability, the variety of knowledge sources and contexts is a key aspect that you want to be able to support. And so you want to have standards and interoperability with strong semantics. You also want to have defeasibility to have a robustness. And classical is super brittle. It's like a big bubble is one way to think about it. It breaks easily. If you have one inconsistency, one conflict, then anything is entailed. Any conclusion is sanctioned in classical logic. And that is just really incompatible with practical engineering of systems for many purposes. LP also has high compositionality, fundamentally due to its semantics, due to that, and this locale notion. Explainability, it has a natural deduction style of proof, so-called intuitionistic, which makes it very good at supporting automated generation of explanations, which people with a high school education can understand. So, for example, have been exposed to Euclidean geometry proofs. Another key aspect in terms of these desiderata is that it can be extended to principled uncertainty of conclusions with strong semantics, including extensions for probabilistic, fuzzy, defeasibility, and a kind of bounded rationality called restraint, which is essentially based on don't care. And again, in this regard, it is far superior to classical logic. And following sessions in the summer school are going to be talking about how to do principled uncertainty of conclusions in a way that kind of reaches out its arms or comes from and bridges to machine learning. So we can think at a high level about the spirit of LP. And there are some important differences from classical logic, for example, first order logic, FOL. One is to avoid oring, that is disjunction, of positive literals in the heads of rules, the then parts of rules. So avoid those as expressions, and as well in intermediate conclusions and therefore final conclusions. And so in particular, you conclude that either A or B only if you either conclude A or conclude B. So that's a kind of meta step where we're bringing in a kind of property of the proof theory into the behavioral specification and essentially semantics of LP, that is proof theory as compared to a classical type of approach. The reason to do this avoiding is, as I mentioned, that permitting these disjunctions creates exponential blowup, and even in the propositional case of FOL, produces NP hardness, in other words, intractability. And that's true for many other KRs that expressively add disjunction to LP with negation. So there's no unlimited reasoning by cases, therefore. Another aspect of the spirit is to, we could summarize as stay grounded. Avoid drawing conclusions that are irreducibly not ground. Ground in the sense of eliminating, being free of logical variables. So in other words, be groundable. As a result of these two aspects of the spirit of LP, it, unlike classical logic, is straightforwardly extensible to both so-called logical non-monotonicity, defaults or defeasibility or argumentation or exceptions, including via negation as failure, also known as weak negation or default negation, and also straightforwardly extensible to procedural attachments, including external actions. And those are key in practical systems engineering that uses logic for example, business rules or a lot of things that people do around databases. Okay, so I'm going to do a whirlwind tour next of some basic logic concepts. Syntax is what is the language for both assertions and for conclusions, and thus for queries as well. Semantics is the meaning of the assertions defined in terms of how they sanction conclusions, which are principles essentially for decomposing the truth of sentences and defined in terms of models, typically. And that'll be true of all the KRs we're talking about here. A formula is in the sense of a well-formed formula that you've probably been exposed to in classical mathematical logic, built up from primitive language elements, such as so-called constants, variables in the sense of logical variables, predicates, and functions in the sense of logical functions. And they're built up via connectives, for example, and, or, not, and implies, and quantifiers, such as there exists and for all. Now, the quantifiers each technically have one logical variable. So we talk about a particular existential quantifier, which has an associated single logical variable, and also the quantifier has a scope. So I'm using color here as a kind of key to some of the pieces of a formula. So here we have the formula for all P1, there exists a P2 such that P1 is a parent of P2. So here parent of is a predicate, it's kind of truth valued. It gets a truth value. P1 is a logical variable. P2 is a logical variable, and we use the convention of prefixing logical variables with a question mark. An atom is the application of a predicate to a tuple of arguments. So we saw that in the example expression that parent of P1, P2, that is an atom. The tuple of arguments has an arity. In the case of parent of P1, P2, there are two different arguments. However, more generally, a predicate can have 0 up to any constant number of arguments. Each argument is a so-called term. We're going to learn what a term is on the next slide. Semantically, the predicate, an atom, has a truth value when interpreted semantically. A truth value could be true or false, but also more generally in KRs, it might be something like undefined, which is essentially can be viewed as don't care. It might be a probabilistic value, such as 0.4, or a numerical interval, such as 0.6 to 0.8. It might be using discretized ordinals in a lattice or something like that, such as unlikely or very likely. There may be multiple flavors of falsity or negation. So importantly, in extensions of logic programs, there's both a weaker and a stronger form of negation known as NAF and neg respectively. Typically, there's a partial ordering among truth values. A predicate is a symbol token or some other, more generally, term, and also has an arity, n. It's also known as a relation. So for example, and we think of the predicate not only as the token kind of name, but also the arity. That combination is what specifies a predicate precisely. So for example, we could say that Sylvester is a cat. Here the predicate is cat, Sylvester is an argument that is an object constant, which we mentioned in green up here when talking about formulas. And another example would be descendant of with arity 2, or between as a predicate with arity 3. There's, say, two objects and the third one is in between them. It might be that the same symbol token has different arities. So for example, employed by could be applied with arity 2 to assert that Alice is employed by Starbucks, or might have arity 4 as in Alice is employed at Starbucks as a barista as her job role or position title, and 2019 as the time parameter of her employment. Now, if you're less familiar with logic or KR, you can think of a tensor with dimension n as having a similar structure to a predicate. Next, let's talk about term. A term is either a constant or a logical variable, or more generally, apply a logical function to a tuple of arguments which themselves are terms. A term looks similar syntactically to an atom, but it designates an abstract object rather than being truth valued. I covered logical variable. A constant is essentially a symbol token. It could be one of the usual types like integer, real, or string, etc. But it doesn't have to be. It could be more abstract than that. Made up symbol name, for example, user-defined types, etc. A logical function that doesn't take any arguments, that is, has arity 0, is called an object constant. A logical function looks similar to a predicate, has an arity, it maps, but it designates rather than evaluates or computes in the way that functions that we talk about in like general mathematics or logical, or in programming language evaluation, we think in terms of. So an abstract, it's a rather abstract kind of function. It's also known as a constructor. So for example, the logical function successor with arity 1, we could say that there is an element or object constant 0, and there's a term successor of 0, referring to, say, the next number in a number line, and then successor of 0, and so on. Battery of with arity 1, as in battery of my cell phone, could be used to designate something. That's a convenient kind of way to name things. Or, for example, the function resulting state with arity 2 takes a previous state and some action into resulting state for reasoning about actions and causality and, for example, planning or robotics or whatever. Ground means lacking logical variables. Propositional means that arities are all 0 and there are no quantifiers. So the more general sense of propositional is something that is equivalent or isomorphic to propositional, that is ground. So sometimes it's used, propositional is used in the sense of ground. And that's a bit confusing, and that's why I'm calling it out explicitly here. In first order logics, or KRs, a predicate must be a constant. Itself must be a constant. That is, pin it down as a particular symbol token is one way to think about it. However, in higher order, that restriction is relaxed. A predicate can be any term. So for example, we can think about the following expression, which has two arguments, a from node and a to node, where the predicate is defined as a logical function, transitive closure of, applied to a logical variable, which is an edge relation, such as child of, or perhaps likes, or is socially acquainted with. Those would be three examples of edge relations. And then we have transitive closure of as a function applied to that edge relation, which will, with some suitable rules that axiomatize it, generate all the paths through the graph defined by that edge relation and some nodes. So here, this expression, transitive closure of the variable edge relation, is itself a predicate. A literal is either an atom or a negated atom. A clause is a disjunction of literals. A Skolem term is one that represents an existential variable for inferencing purposes using a newly introduced function. A model is an abstract structure that assigns truth values to assertions and conclusions. And there's a cluster of things that are used to define model associated with it, such as a model satisfying a sentence. If the sentence is true there, that's called satisfaction. Satisfiability of a set of assertions. Model theory is about the characteristics and principles of models. And an interpretation in model theory means a candidate model that is being considered for whether it does satisfy sentences, etc. Entailment is another key notion, and it means a set of assertions or models sanctioning a conclusion. And inferability is in the sense of deduction via some kind of proof procedure. So that's distinguished from entailment because it's not about the model theory directly. It's in terms of so-called proof theory, which is about abstract proof procedures, typically constructive but possibly infinitary, and their correspondence to model theory. An inference algorithm is a proof procedure that's implementable on a computer. Soundness of proof theory is that if something is inferred, then it is entailed. Completeness is the other direction, that if it's entailed, then it will be inferred. A universe, in the sense of logic and KR in both classical and LP, is an interpretation aspect or portion or abstract portion of an interpretation or model, which specifies a domain of discourse. That is, a set of abstract objects that can be the instance of a logical variable. A Herbrand universe is the set of ground terms that is formed from object constants and other logical functions. It's infinite unless functions all have arity 0. The Herbrand base is the set of ground atoms, and the Herbrand interpretation or model is one defined over the Herbrand base. And that's a crucial notion in the definition and also for some of the advantages of LP and its extensions relative to classical logic. Forward inferencing means a proof procedure that works from assertions toward conclusions, including via intermediate conclusions, also often known as forward chaining. Backward inferencing or backward chaining, also known as goal-directed, is a proof procedure that that works from a goal, for example, an original query, towards assertions via intermediate subgoals. Exhaustive forward inferencing, you're generating the entire set of conclusions. Obviously, that's usually more expensive computationally than goal-directed inferencing. And largely because of that, proof procedures for dealing with larger scale knowledge bases and in practical settings are usually more forward than they are, more backward than they are forward. But there's also mixed direction, which is a combination of forward and backward, and we'll get to that a little bit later. In query answering, a logical query is answered by inferring what instances of the goal formula or expression are true versus false, or more generally, inferring truth values for the goal instances. A control strategy in a proof procedure controls its search aspect. Resolution is a very important kind of proof procedure in both classical logic, LP, and its extensions. In classical logic, resolution works by first converting given assertional knowledge into clauses, but also converting into clauses the negation of a goal, skolemizing if necessary, and then seeking to prove a contradiction by so-called refutation. That is, by deriving new clauses via a special resolution inference rule, where we take two clauses that share a common literal, where one has it positively and the other has it negatively. You can think of it as an atom and its negation. And then the resulting clause we get rid of those literals, and we have a big or of all the other literals. But where an empty clause represents contradiction, you're seeking to prove a contradiction. Whereas LP and extensions thereof get creative and modify this kind of resolution. As I mentioned earlier, it steps back from trying to prove things by contradiction because that is perfectly brittle. So in terms of directions of reasoning, for direction, you're recursively working to draw more conclusions. After you've drawn some conclusions, in backward, you start from a goal, recursively work backwards via subgoals to other subgoals, eventually to assertions. And both chain through intermediate conclusion steps, underlying is a search for useful, valid chains of reasoning. Pure backwards is usually more efficient because it's more focused than pure forwards is, but mixed direction, that is a kind of hybrid, is often superior to both pure backward and pure forward. And semantics means that whether you're going forward, backward, or mixed, you're going to, if you respect that semantics in your proof procedure and proof theory, then you're going to get the same results regardless of what the so-called control strategy is for doing the search. Now, it is important to understand that for a given logical KR, inferencing usually has significantly lower computational complexity when restricted to the propositional case as compared to when there are logical variables. So for example, propositional versus first order classical logic, propositional versus first order logic programs. And you can think of neural nets as propositional, essentially. Horn FOL is defined relative to the clausal form of FOL. A horn clause is one in which there's at most one positive literal. So here, H and the B sub i's are all atoms. This symbol, the upside down, the sort of V here, means or. This symbol before B1 means negated in the sense of strong negation in classical logic. This is also known as, if you have one positive literal in the clause, that is also known as a definite clause or so-called rule. A special case of that would be where you just have a single atom as a literal, say with no logical variables. That's called a fact. There's also what's known as an integrity constraint, where there's no positive literal. A definite clause can be rewritten equivalently as an implication. H if the conjunction of the B sub i's, where the B sub i's and the H, once again, are atoms. The H part is called the head. The conjunction of those B sub i's is called the body. And this is a convention in LP that rules are defined in the form head if body.
Benjamin,
Yes.
sorry, would it be possible if we can stop at 9:55, take few questions and then restart?
Sure.
Okay.
Thanks for the heads up, Asim. An integrity constraint can be written as an empty head rule. And here's an example of Horn LP with some reasoning concepts associated. So we might have some assertions that Socrates, Anne, and Peter are each a human, that Anne is modern, that Socrates is educated, and then we have some rules that if X is human, then they're mortal. If they're fallible, if they're mortal, a given Z, someone or something is educated if it's human and modern. If W is fallible and educated, then W is humble, let's say. And then we could do forward chaining to infer from these given facts through one rule application of a rule that say mortal if human, we can conclude Socrates, Anne, and Peter are all mortal. And in like fashion from the rule about fallible if mortal, that Socrates, Anne, and Peter are all fallible. And from the rule about educated if human and modern, that Anne is educated. And then in like fashion, get that Socrates and Anne are humble. Now, if we enter a query and do backward reasoning, say the query humble of P, where P is a logical variable, with a query expressed using this question mark dash, then we're going to get a couple of answers that P with the instantiation to Socrates is humble. So that is an answer to the query. And that's known as a binding of P to Socrates, and ditto for Anne. We could think in terms of the subgoals going backward from the query humble of P to through the rule about humble. We have a subgoal about fallible and another one about educated. We see that displayed on this next line here, which is just a way of depicting that. And then backward chaining from fallible, we can get to mortal, to human, and then to some instances that satisfied human. And back chaining from the query educated, we get Socrates directly from a given fact assertion, but also via human and modern, we're able to get some bindings which imply that Anne is one, because human and modern are anded together, and so on. And we also and together this subgoal chain around the fallible subgoal for the three instances, Socrates, Anne, and Peter, and so on. So that all gets put together, and I don't really have time to go through all the details of that here, but there's a lot of good available pedagogical material about backward chaining and forward chaining proof procedures. Okay, so Asim, I'll stop here for now. We're most of the way through the session, one part of the deck, and we'll cover the rest in the next hour.
Okay, so Benjamin, there are several questions. So starting from the first, can you provide a use case for KRR?
Well, there are many. So for example, maybe you're trying to reason to generate a conclusion about what is allowed or not, or what the prices of goods are in supply chain, or whether you're in compliance with an organizational policy, or whether a given medical treatment is suitable to a patient's case and situation that they present with.
Okay.
Those would be a few examples of uses of KRR.
Thank you. The next question is by Helio. It says, are so-called embeddings considered a form of knowledge representation? What are their limits and applicabilities? Can we human explain them?
That's a very interesting and important question. You can view an embedding essentially as a kind of abstract structure or a means of assigning or mapping to truth values, or a pair of things to a distance. And some of the later talks in the summer school is going to be treating the issue of how to view embeddings and similar kinds of things that are used in neural nets or machine learning to the logical notions of truth that I was talking about here at a more basic level. And can humans understand them? Yeah, kind of, sort of. I mean, they have a certain kind of softness, or you can think of it as fuzziness, or kind of mapping complexity associated with them. So to some extent, humans are not able to communicate very concisely or crisply about them beyond a certain level of kind of vagueness of correspondence that's not captured in a way that people can share with each other terribly well explicitly. But that can be a strength as well as a weakness.
Okay, it's difficult to take all the questions, but let me go to the next one. Can you be more specific on why NNs are essentially propositional?
Yes, so in neural nets, you have these different units, and you have a fixed number of them, and you're doing arithmetic operations on values associated with the activation level in those units via the weights, etc., and things like a sigmoid or a ReLU type of transformation on values also. But relatively simple kinds of weights and functions and so on that combine them, as opposed to having an abstract space that is defined implicitly in a way which is much larger than you attempt to instantiate in a materialized fashion as a data structure. So in that sense, it's propositional.
Okay, great. Thank you. Let me take the last question. So does human perform reasoning in a forward-backward manner? It seems we most of the time jump to the conclusions or somewhere near them rather than step-by-step inference. Is it possible to implement such a model for reasoning?
It is. However, part of the value of KRR is that you can get down to a fine-grained level, blow by blow, to examine and validate whether conclusions are indeed sanctioned and therefore indeed correct relative to some given information. That's a really crucial thing in systems engineering generally, that if you, to the extent that you have a detailed specification, you're able to demonstrate that you're abiding by it, or at least get closer to that practically.
Okay. Thank you, Benjamin. You can continue, and at the end, please leave 5 minutes or more for question answer.
Okay. Okay, so moving on, we're going to get to session 2. If you've just joined, we're in the middle of 2 sessions, Intro to Practical Knowledge Representation Logic, just finishing that and going to the second session, State-of-the-Art Practical Reasoning and Meta Logic. Okay, so we just did an example of Horn LP. Now consider how that relates to Horn FOL. So we have a similar definition syntactically, the Horn case of FOL. So consider the following set of assertions, that if X is a predator animal and Y is human, then X is dangerous to Y. If X is a lion, then X is a predator animal, and the fact that Simba is a lion and the fact that Joey is a human. So doing an iteration, applying just one rule, we get in the constructive bottom-up least fixed point style of semantics or exhaustive proof procedure, that Simba is a lion, which is included just from the assertion, and ditto that Joey is human. But then in the next, from an application of a rule, we get that because Simba is a lion, Simba is a predator animal, and that is added to the set of intermediate facts that are accumulated in a bottom-up constructive fashion for doing exhaustive while doing forward inferencing. We can then conclude from the other rule that Simba is dangerous to Joey, and so on. Then we have, in the next iteration, we reach quiescence, we reach the fixed point, and the model, so-called, is this set of ground atoms in LP. Now consider the Horn FOL rule-based version of the set of assertions above, where the classical implication connective replaces the colon dash that is used in logic programs, LP. Then the ground atomic conclusions of PF, this Horn FOL version, are exactly the same as those in M of P above. That is, that set of ground facts that are concluded in LP and that are in the model. PF also entails various conclusions that are not in the form of ground atoms. For example, so-called non-unit derived clauses, such as Simba is dangerous to Y if Y is a human. All the tautologies of first-order logic, such as that Z is either human or not human, and various kinds of combinations of non-unit derived clauses and tautologies. For example, that if Simba is not dangerous to Y, then Y is not a human. And because of there being these other conclusions, that's one way to help understand how FOL is richer in terms of the space of conclusions, but than LP. But LP is maybe capturing all the conclusions and inferencing and entailment that you really care about for a given set of rules. And that's the case, for example, a lot of uses of Horn LP in semantic web and in databases, in knowledge graphs, and in business rules and many other applications. The concept of logical monotonicity is that if you take a set of assertions and then you grow it to a superset by adding one or more assertions, then the set of conclusions that are entailed in a given logical system, that logical system S, is also a superset for P2 of what it was for P1. In other words, that when you add to the set of assertions a set of conclusions, non-strictly grows. One does not retract conclusions. And this is very good for pure mathematics. There was a famous movie line, being in love means never having to say you're sorry. So we have the version of that for classical mathematics, that proving a theorem means never having to say you're sorry if you add more axioms or postulates or assertions. In normal LP, we add a new connective that is weak negation. And we add it to Horn LP. Normal LP is also known sometimes as ordinary LP, corresponds roughly to the syntax of Prolog. The syntax is generalized to permit body literals that may be naffed. So the semantics has subtleties for the fully general case because of the interaction of negation's failure with recursion, i.e. cyclic dependencies through rules among different atoms. A lot of theory was developed about this during the decade from 1984 to 1994, and it's been well understood theoretically since then. So here's an example of LP with NAF. This is purely fictional. Say there's some product such as a Sony 5401 electronic widget, which at Amazon on a given day for a given customer is $49.99 if the customer's in the US, the day is in the month of October 2004, and the day is not a sale day. The price is $39.99 in similar circumstances if it is a sale day. And then we can think about some facts about there's a particular couple of days in that month, say the 12th and the 30th of October in 2004. A couple of customers, Barbara Jones and Salim Birza, who are in the US, and that the 30th, say, of October is a sale day. So this set of assertions in normal LP entails, among other conclusions, that the price for the widget for Barbara is 49, whereas the price for Salim is 39, because for Barbara we were talking about the 12th of October, whereas for Salim we were talking about the 30th. So if we consider this rule base and then we update it to add a new assertion that the 12th is also a sale day, then something that was concluded before, namely the price for Barbara was 49, is no longer entailed. It is retracted. This is called non-monotonicity. Instead, it entails that for Barbara, the price is 39, just as it was for Salim. Now, weak negation or default negation or negation as failure is often known, is the most common form of negation in commercially important rule and knowledge-based systems. It may appear in the body, but not in the head, and the intuition or concept for it is that Q is not derivable from the available assertions information. That is, one fails to believe Q. I know I do not believe Q. But you might also not believe Q to be false in a strong sense of the opposite of Q, which is the notion known as strong negation or explicit negation, that extensions of LP, for example, RULOG, inspired by classical negation use. So there's two different flavors of negation, and when you have this kind of strong negation, that brings the potential for logical contradiction or conflict, because you have a showdown and a kind of exclusionary, it's got to be either or between P and the strong negation of P. Okay, so let's move on to the state-of-the-art practical reasoning and meta-logic. So again, in case you joined us later, this slide set is subsetted from a longer version that will be posted on the web. It's about 3 times longer. So if we look at the landscape and industry of practical logic, LP is the core KR of structured knowledge management today. I want you to really think about that, really let that sink in. You may have been exposed primarily to classical logic previously, but it is not the main show in town. Relational databases are subsets of LP, a key restriction there being function free. Knowledge graphs are essentially the same subset of LP as a logic that relational databases are. So for example, graph databases in Sparkle or some of the other emerging things such as a graph query language or older such as XQuery and XML, those are also subsets of LP. The so-called business rules sector in commercially in industry, business rules engines or management systems, things like production rules, event condition action rules, DRULs, etc. More precisely, their logical subsets are subsets of LP. Prolog, more precisely, its logical subset, also often called pure. So one of the largest applications ever created in the history of the Earth is the so-called automated targeting system of U.S. Customs and Border Patrol, which acts as essentially the cell membrane for the entire United States, both in terms of economy and people. And it is built using tens of thousands of rules in Prolog over when conventional imperative programming languages such as COBOL and C++ could not really fill the bill. I had it as a teaching case, the failure of such approaches back 20 years ago when I taught at MIT in the business school. Other subsets of LP include things that are in the semantic web space, such as ontology standards, RuleML, RIF dialects, which are in turn based on RuleML as a standards design from the World Wide Web Consortium, RDF schema, etc. Now, there are other important KRs in the industry, but they're much less important overall than LP as a group or as an umbrella. So some subsets of classical logic, so propositional used for circuit design and hardware, and satisfiability for planning. First order logic is often used for program verification. There are various other things that are pretty niche or not so commercially or practically important that are, say, temporal logics, modal logics, and the so-called description logic subset of FOL, which Al was originally defined in terms of for web ontologies and knowledge graphs, but essentially failed to achieve liftoff in industry until OWL was recast in its version 2 to be based on LP rather than on the description logic subset of FOL, but intersecting with that subset in the same way that Horn LP intersects with Horn FOL or corresponds to. Now, there are some emerging other KRs that are extensions of LP rather than subsets of LP, including RuLog, which combines several major LP extensions, and the probabilistic LP cluster, which we're going to be hearing more about in later sessions today and in the summer school. And then there's some others that are not so commercially or practically prominent as yet, but are very useful for certain kinds of things, say answer set programs, which supports combination of logical reasoning and combinatorial problem solving. That's closer to classical and has scalability limitations more in the direction of classical as well. So there are some state-of-the-art tool systems relevant to neurosymbolic that are all open source that are listed here. These are based on LP. One is XSB. It's actually an extension of LP. originally from Stony Brook, but multi-institutional. It's a full programming language that is essentially a Prolog++, and it pioneered a lot of sophisticated inferencing techniques such as tabling techniques and so-called well-founded semantics, has good soundness and completeness properties overall. Another Prolog, which is can be viewed as extended LP, at least when you employ it in a pure fashion, both XSP and SWI Prolog, is SWI Prolog. It's the most popular Prolog or Prolog++, but it's less expressive and complete than XSB somewhat. It does collaborate and swap code with XSB, and it brought some of these sophisticated techniques from XSB in 2019 came into SWI Prolog. I was involved in that along with some collaborators. Janus is a Python XSB interface that's bidirectional, recently developed. It's speedy and easy to use. It combines tightly Python and Prolog, and optionally both of those could be implemented over C and combined well with C, for example, then with Ergo AI on top. Ergo AI is a Rulog system, so it's really significantly more extended than just XSB or SWI are as compared to basic LP. It's a full programming language that's XSB++, therefore we could kind of think of it as Prolog+++. And it tightly combines expressive extensions, for example, for higher order syntax, defeasibility, restraint, bounded rationality, and others, and gets those to work together well without much restrictions on how those are combined. Another cluster is probabilistic logic programming. One system for that is Problog2, which extends LP with probabilistic. That's Bayesian uncertainty and has ML with it or on top of it. Ditto for PETA and the CP-lint system developed on top of or using PETA or supersetting it, and Plow, which is an extension of the PETA portion. PETA won the Test of Time Award in the logic programming community a couple years ago. That supports non-Bayesian as well as Bayesian uncertainty and also has capabilities for ML. Now, in general, there are a number of desiderata that are important for neurosymbolic or for combining KRR with ML. And in the choice of KRR, the design of KRRs, and the choice of how to hybridize or combine KRR and ML, there are trade-offs. So it's important to seek Pareto optimal sweet spots. You're not going to get everything you ideally want. So one cluster that is a sweet spot is the Rulog ELP. Another is the probabilistic cluster. And Rulog combines several major expressive features, good soundness and completeness, as I mentioned, also strong explainability, strong modularity, and orchestration, robustness in the face of conflict, so excellent defeasibility characteristics and expressive power, attractive computational scalability, which is polynomial using the bounded rationality feature, and actually better than pure basic LP itself, interestingly. Many other optimizations, and it has a commercial quality engine implementation in open source called Ergo or Ergo AI. It uses a stack of transformations to define the semantics and also implement on top of XSB, and XSB in turn does that over kernel, which in turn is implemented in C. There's this speedy, easy to use bidirectional bridge, so you can compose XSB or its superset Ergo AI on top of it with machine learning, with NLP or other components and services. So many of the AI components that are state-of-the-art today are in Python. So this is a really major strength of this group. In current work, there's work going on to integrate more tightly and extensions for probabilistic and machine learning via PETA and CP-lint and Plow. Now, as I mentioned, there's also this other cluster, including Problog2, which is a re-implementation of Problog, but implemented in Python rather than Prolog. It has some ML tools too that work with it, or part of it, is depending on how you think of it. PETA, ditto. Fabrizio Raguzzi, in his book Foundations of Probabilistic Logic Programs, second edition from last year, is a very good source of research knowledge about this probabilistic LP cluster. Plow is an extension of PETA that cross-fertilizes with RULOG and combines Bayesian and generalized fuzzy or so-called triangular norms via intervals, uses some of the other features that are in RULOG, as well as can support some other kinds of uncertainty and weighting. And that is in progress. The first version came out a few years ago. Some KRR technical challenges are first and foremost, combining high expressiveness and computational scalability. So speaking for myself, I've been working in research in AI for 40 years since I was a graduate student at Stanford. And when I entered the field, people had a wish list for expressiveness. And they made an assumption that it would all be a superset, of course, of first order logic. Well, you can actually have everything they had on their wish list, pretty much, except be a superset of first order logic for the reasons I've already discussed. Because being a superset of first order logic, even without adding all those other aspects of expressiveness, higher order, meta, etc., defeasibility, and so on, blows you out of the water in terms of computational scalability. Interoperating between multiple KRR approaches and systems is also a major set of challenges in KRR. And so standardization is important. Realizing the relationships semantically between different KRRs, which are originally described differently, has been key to the progress in and success to date of knowledge graphs and other things in semantic web, for example. Combining tightly many KRR expressive features in one overall KRR, one motivation for that is flexibility. Another is to be an umbrella for interoperation. And that is a third major challenge in the area of KRR overall. Finally, probabilistic as an expressive feature of KRR is key as a potential and also really required bridge between ML and KRR. But if you have unrestricted Bayesian probabilistic as an expressive feature, then you get intractable computationally when you try to combine that with LP or some other medium to high logical KRR expressiveness overall. Now let's talk in more detail about computational complexity, try to understand what's going on with it. The propositional case I mentioned is NP complete. That was the original NP hard problem from over 50 years ago now. First order, both in classical and LP, inferencing is undecidable. Now, why is that? That's because as soon as you permit logical functions with non-zero arity, then the Herbrand universe and the Herbrand base become infinite. And essentially what's going on is you have this capacity for cyclic dependence, known as recursion, through logical functions. For example, as we saw in the example about successor of 0, successor of successor of 0, successor of successor of successor of 0, through the rule that if x is a number, then successor of x is a number. So just all the objects that we're talking about that are potentially arguments of the number predicate becomes infinite. However, if we restrict to the Horn case, propositional Horn LP goes all the way down from NP complete to linear in the size of the assertions. In the case of normal LP, where we take Horn and then add negation as failure, inferencing is quadratic, in practice nearly linear. So that's some pretty good news. However, if you do not stick to the well-founded semantics for negation as failure, then you don't have nearly such nice tractability. I don't have time to go into answer set programs much, but I think that's an important observation. Now, suppose we go from propositional to first order in normal LP. Remember, normal LP was, for the propositional case, nearly linear, was quadratic. So here, grounding the LP increases the LP size due to each variable in a rule may have multiple instances, the set of ground terms. And each predicate and function may have multiple arguments, and functions may be recursively applied. So, boom, you're not decidable. But even if you did not permit logical functions with non-zero arity, logical functions at all, then you get to a much higher degree of polynomial complexity. So we'll call the BR restriction in LP and its extensions that a rule or query has a constant bound on its size syntactically. And this implies a constant bound on the number of distinct variables per rule, constant bound on the arity of the predicates and functions appearing in the rule. And for human authored rules, BR and BV and BA are typically met in practice and not very onerous expressively. So V is like order of magnitude 10 rather than 100, say. K is order of magnitude 10 rather than 100. An important restricted case of first order normal LP is function free. And in that case, the ground LP is polynomial in size of the original LP, and thus inferencing is polynomial. However, prohibiting functions is pretty onerous expressively for many purposes. It disallows, for example, higher order syntax, therefore efficient defeasibility, scolomized existentials, rulog, and a number of other things. However, a key idea to the rescue is that we can use restraint, which is an extension feature in LP Plus pioneered in rulog. For example, the radial form of restraint. Restraint is bounded rationality, and it uses the undefined truth value, which essentially don't care truth value, and all ground atoms whose size is beyond a constant bound called the radius are treated as having don't care truth value. So for example, when we were talking about successor of successor and successor of, maybe like in communication, humans often might stop at around radius 3. Or if we're reasoning about time steps and reasoning about action, for reasoning in planning, maybe we don't care beyond 1,000 time steps. And so we might have a radius of 1,000. So the restrained Herbrand base is polynomial, and this is a fully semantic form of bounded rationality. It's not based on the proof procedure, which was the basic idea behind previous attempts to define bounded rationality operationally in KRR. It's efficiently implementable with low overhead, and for human readable rules, size of under about 30 suffices often in practice. One way to think about that is 30 is about the max number of words in a natural language sentence before beyond which it's not really onerous to break up the sentence into multiple sentences in natural language. Now, first order normal LP in practice, this radial restraint plus the BR restriction keeps inferencing polynomial. And this is the same qualitative complexity class as relational databases and knowledge graphs. I want you to let that sink in. No more complex computationally, qualitatively than relational databases and knowledge graphs. And the same is true of rulog. With higher order, with defeasibility, with scolomized existentials, many other expressive extensions, although not with unrestricted Bayesian. And the expressive extensions in rulog are carefully designed to ensure this. But you fall off the cliff of tractability if you put in unrestricted Bayesian probabilistic. So therefore, one needs creativity and care in the design of KRR to incorporate probabilistic with computational scalability. There are some approaches to date that do this. There's also non-Bayesian approaches, particular T-norms, as the so-called truth functional combinations as the semantics for and or, and that is a way to address this. Function free is a commonly adopted restriction in practical LP or web rules today in not only database query languages and business rule systems based on production rules or similar event condition action rules, but also OWL, the ontologies in semantic web, and some other things in semantic web, such as basic sorts of semantic rules that are often used in combination with knowledge graphs. But functions are often needed for applications over the web and in other realms, including to do skolemization to represent existential quantifiers. So here's an example. We might say that there exists a P such that P is a part of C and P is a nucleus if C is a eukaryotic cell. In other words, if C is a eukaryotic cell, then it has a nucleus. A nucleus exists for it as a part of it. And we often want to rewrite the rule with skolemization to look like this, that if C is a eukaryotic cell, then there is an object, a skolem term, with a newly introduced skolem function applied to C that is a part of C, and that skolem term is a nucleus. And related to this is convenient naming. So for example, to be able to have a named logical function such as steering wheel of, which might be applied to an object as its argument, such as my car. High-log and reification, that is higher order syntax, also require logical functions for many purposes. We'll see a list of that later. Data types and data structures, some aspects of that to capture their semantics in a technical sense, you actually need logical functions, for example, lists. Functions in LP lead to undecidability due to the potentially infinite number of conclusions, as in the successor and number example. The practical effect is that one may get runaway computations during inferencing to answer a query. And this has been a significant pain point in FOL and other classical logic reasoning that is theorem proving, including in higher order. Logic programs, Prolog in particular, there was a huge amount of work on trying to ensure at least termination. And this kind of runaway infiniteness happening in an unforeseen fashion when people write a bunch of rules. The heart of the problem, though, here in terms of why functions lead to, or how they do lead to undecidability, is the semantics, not the proof procedure or the implementation. It's not that semantics are problematic so much as the expressive richness that you're combining with the usual intuition for doing semantics. Now, a kind of sophisticated technique that has been developed in LP and RULOG, which helps with logical functions, but also helps with a lot of other aspects, including reasoning soundly and completely about negation in the presence of negation as failure, is so-called tabling, which builds and maintains a forest of attempts of inferring subgoals and what the results so far of those attempts on the subgoals have been when doing mixed direction inferencing, mainly backward direction. It's caching. You can think of it as doing dynamic programming. So it's mixed direction because it brings in some forward direction reasoning in addition to backward direction, or and it caches in a smart way. And these algorithms are pretty efficient, including in their low-level data structures and indexing and so on. Now, challenges requiring algorithmic sophistication include reasoning in the presence of logical functions where terms can be complex and you have unifiers among terms and variables that can be complex. When you're doing higher order syntax, so-called higher order for short is how we'll talk about that here. The indexing requires modification to be efficient. And in the presence of non-monotonicity, in particular default negation, and also more general forms of defeasibility. So techniques have been developed to meet all of these that do efficient control of search, efficient indexing, efficient low-level data structures, and for example, to be dependency aware when updating a set of assertions and then querying against the the new iterate of the set of assertions without having to throw away most of your previous inference results, and therefore being able to do fast updating, including to have an edit test loop when doing rule authoring or rule debugging be interactive response time. So there are a set of methods that are highly sophisticated, have been optimized over the last 2 decades. And many people have felt like, oh, I can implement a rule engine and algorithms. It's simple. I'll just do it. And then they end up in hell because they didn't realize some of the complexities that can arise, bite them, and they are not making use of the best practice or the available open source code. Functions in LP, restraint, the bounded rationality approach. The intuition, as I mentioned, is don't care. It might be that you can't figure it out or you don't want to figure it out. And we can think of there being, think about the set of all literals, and some regions within that set are misty in regard to truth value of whether it's true versus false in the weak negation sense of falsity. And radial restraint, you have this fixed radius. Every literal whose size exceeds the radius is concluded to have misty truth value, in other words, undefined truth value, written U for short. And the size here is just an abstraction norm metric on terms, could be term size, term nesting depth, or similar. And so, for example, if we set the radial restraint, the radius to be 3, then whether successor of successor of successor of 0 is a number is just left as undefined. Radial restraint as a proof theory incorporates straightforwardly into algorithms as modest computational overhead, about 10% in experiments we've run at scale. And the undefined is also useful for treating semantically paradox in the so-called unstratified case of logic of ordinary or normal LP. In other words, unstratified negation is failure. There are several other kinds of restraint, skipping or don't care about particular instances of particular rules. For example, when reasoning causally, it might be that you do an external query and it doesn't return. You can treat that as having an undefined result. The treatment of safety, which is a technical concept and condition on rule bases, both in regard to NAF and also in regard to so-called sensing, i.e. external querying. It might be that some external source is not willing or able to answer query because it has too many unbound variables. Like if I try to externally query a company Blue Pages phone directory, it may not give me permission. You have to either specify a particular person or a particular phone number, but they're not willing to dump their entire Blue Pages in answer to a query. Another place where restraint is useful is in probabilistic uncertainty. CF, the plow extension of PETA and CPLint. So for example, we could call that joint loosening, where we have a don't care about conditional correlation, which results in widening the intervals associated with the numerical uncertainty of some joint that is ANDed formula. Again, this only requires modest computational overhead, and high log is another key extension or feature in RuLog and a number of other KRRs, including that extend LP. It's a higher order extension of predicate logic, which has a tractable first order syntax. So it allows certain forms of logically clean yet tractable metaprogramming. Syntactically appears to be higher order, but semantically it's first order and tractable. So you can permit a predicate or function to be a variable or indeed a complex functional term. And a rather elegant transformation defines the semantics and is used to implement it, along with some indexing techniques that are specific to high log or higher order that help increase the efficiency of the implementation. So it's simple enough to state on a single slide here. The high level spirit is if we have some literal, a predicate, say, being applied to 2 different arguments, that's rewritten, is transformed into another literal, which has a particular predicate where the predicate is not a variable. And then the predicate variable becomes an argument along with the original arguments of that newly introduced predicate. When I was a grad student, this was called the holds trick. About 10 years later, this was developed by Chen, Kiefer, and Warren. So a simplified version of the transformation, which gives the intuition, is to rewrite each atom, say that has arity 2, using a particular new predicate, holds for arity 2 originally arity 2 predicate, where we have generic predicate constants, holds and holds 1 and holds 2. So we have a particular set of those. Usually you don't have so many, such a huge arity. So, order 10 is about the max practically that is non-onerous to stick to. And you can treat each term in a similar manner where you have a generic function constant particular to the arity, and then have a set of those. Again, you can have a limited number of them, say approximately 10. And high-log then permits variables over predicates and function symbols. For example, in this rule here, P of xy, if x of az and y of zb, x is a higher order variable, sometimes called a meta variable, which is ranging over predicate names of arity 2. Y is likewise such a variable, but z here is a higher order variable ranging over function names of arity 1. High-log also permits variables over atomic formulas. This is a kind of reification, and the higher variable that ranges over function names and over variables more generally could be terms as well. Now, high-log's diffusion, it's been used in ISO common logic, which is the main standard for first-order logic commercially, to syntactically extend first-order logic, and it appears promising for some other purposes in the kind of technical treatment of semantic web and OWL and RDF, for example. It's implemented in Ergo AI and its predecessors, and partially exists in XSB and a number of other systems. Reification is kind of similar in some ways to Spirit, in Spirit to higher order. It takes a term and it takes a formula and makes a term out of it. So we'll write that using the dollar squiggly brace around the formula that you start with, and then the result of that is a term, i.e. an object that designates an object that's made out of the original formula. This was introduced about 20 years ago. So whole rules can be reified as well as formulas that are appearing within rules. Another thing that goes along with high-log and reification, kind of like peanut butter and chocolate, is rule IDs. So this is a simple but important feature. Each assertion statement gets a unique rule ID when this expressive feature is present in the KR. And we kind of take this for granted in programming languages, but classical logic lacks it. LP was defined originally without it. And the ID can be explicitly specified and named, or it can be left implicit. If it's specified explicitly, we'll use a syntax here, @ bang, curly braces, around the ID name, the ID. So if it's implicit, it's treated essentially as a scolem, which you can think of as generating a symbol automatically, known as a gen sim in general in computer science and AI. So rule IDs enable various useful kinds of meta-knowledge by asserting properties about the rule ID. For example, provenance, that Michael was the person who created my rule 17. Also for defeasibility, to be able to express prioritization between different rules. It's a kind of a hook for prioritization precedence predicate to be defined in terms of. Other kinds of rule-based transformations as well. So to be able to do essentially meta-programming at the logical level within a given KR. And that's useful for language extensibility, UI, NLP, explanation generation, and many other purposes in AI. So we'll call high D log the combination of high log, reification, and rule IDs. For meta reasoning, this is useful in knowledge exchange or introspection. Metadata is central to the web. So here we've got meta knowledge or meta reasoning. This is important for what are called modals. For example, believe, permit, should, desire, intend, so-called BDI, belief, desire, intention. Having multi-agents where one agent's belief is, say, nested within another agent, believing whether that first agent believes something, and so on to various levels of depth, or deontics around what is permitted or should happen, and other similar notions such as desire or intend, which are important for preferences, social settings and behavior and applications, and planning and many other purposes, including in robotics. Defeasibility uses HeidiLog crucially for efficient and flexible and analytically clear way of formalizing defeasibility and operationalizing it practically in the state-of-the-art systems. Using the so-called argumentation rules technique, one can encode using HiLog and rule IDs the principles of argumentation or debate. In other words, when a given rule instance should be defeated. That is, an exception should happen relative to that particular rule whose instance we're talking about being defeated.
Sorry, Benjamin, just a
Yeah.
reminder that we have 10 minutes left and then we
Okay.
have 5 minutes for Q&A.
Great. Okay. So I'm getting there. I'm pretty close. Another use is that we saw in the example about transitive closure is for conciseness, but conciseness more generally. HeidiLog is very helpful for. And this is one of the big lessons of Psych, the large-scale AI knowledge base that was built starting in the 80s by Psycorp, led by Doug Lennon. Reasoning control, modularization of knowledge bases, context, including provenance, probabilistic or uncertain, other kinds of uncertainty, about sentences representing natural language, for example, compositionality of phrases, compounding of nouns, adverbial modification, transforming knowledge, for example, in compiling away some syntactic extension features into a simpler syntax that's implemented in a kernel or more efficiently. Flexibility in the tuples of arguments that a given predicate or function has, for example, for representing knowledge or doing reasoning about space and time, and many other purposes. So HiLog and rule IDs and also reification are really incredibly helpful in KRR generally, and arguably really are pretty much required for a lot of purposes, including capturing more complex kinds of knowledge that humans communicate to each other in natural language and socially. Another key expressive feature is defeasibility of knowledge and reasoning. Now, there's a more general concept of defeasibility than just default negation, where a whole rule can be true by default, but may be defeated, that is, have exceptions. It's often called a form of common sense reasoning. RuleLog has defeasibility, but most previous KRR languages do not. And its approach to defeasibility is the most flexible, efficient, and practical. And so argumentation rules, I mentioned before, you can encode the principles of defeat as a set of general meta flavor rules, or you can think of that as debate and argumentation. For example, to represent a cell has a nucleus. There are exceptions, like during the anaphase of cell division, red blood cells never have nuclei. A cell has two nuclei between mitosis and cytokinesis during cell division. Some fungi have multiple nuclei. So there are exceptions. And so if we think about what does this look like in rules, we might have, say, a vendor's rules about ordering lead time, which is a critical aspect in supply chains. We all know that very well from the pandemic, but it's been well understood for decades in the area of B2B e-commerce and manufacturing supply chain, for example. So they may have rules that prescribe how a buyer must place or modify an order, and they communicate those to the buyer as well as using them internally within the vendor. Say that if the buyer is qualified, it's already been checked out as a customer and vetted to a certain extent, then their lead time is 14 days ahead. But if the ordered item is a minor part, don't want to deal with taking it that quickly, and so it's 30 days ahead. 2 days ahead if the order's item is backlogged at the vendor, and the order is a modification to reduce the quantity of the item and the buyer is a qualified customer. So you're easing the squeeze at the vendor, and so willing to take that on very short lead time, because actually in other ways, though it makes some extra work for the vendor, it's saving even more work for the vendor being able to fulfill other orders. And say if the customer has walked in, hasn't been vetted and qualified, then say 45 days ahead, which is really the most comfortable amount of lead time, say, at the vendor. Now, suppose more than one of the above applies to the current order, then you have a conflict. A helpful approach is precedence, known as prioritization, between rules. So D is a kind of catch case. All the other rules take precedence over it, say, but also you might have some partialness of the order of precedence. So among A, B, and C, say we have that C takes precedence over A, the 2-day rule, over the 14-day rule, but no precedence established between either of them and the rule about 30 days if it's a minor part. So that can be encoded straightforwardly. This is using ergo type syntax here. And we express prioritization between rules using a special syntactically reserved predicate, the syntactic reserving being indicated by a backslash, overrides that say the 2-day rule, which we've called reduced tight, has precedence over the 14-day rule, which we called pref cust here. And knowledge generally often has exceptions. And those exceptions or special cases are inevitably realized over time. Knowledge is incomplete, say, multiple authors contribute, etc. And if you're required to enter knowledge at any given time to be strictly or universally true, that is exception-free, is often quite impractical because it precludes stating generalities, the typical, and limits the author pool, and is essentially a category of the perfect being the enemy of the good. Now, exceptions manifest as contradictions, that is conflict, and leveraging multiple sources of knowledge, say when you're merging knowledge bases, large scale socially, for example, over the web, part of, the kind of things that people try to do with interoperability and semantic web as well. You have human errors, you have confusions, you have omitted or underspecified context, and defeasibility is always prepared to handle exceptions, avoids generating unreliable conclusions the way that classical logic does, represents meta-knowledge that resolves the conflict, and notably these priorities, which naturally arise from, say, one source of a rule being more recent or authoritative or reliable than another, or perhaps a rule or group of rules being more recent than others. That's important, say, law and policy, or generally in engineering when you have updates to your specifications. Also, priorities arise naturally from causality. Say you have an action's causal effects override persistency as a defeasible, like ceteris paribus. Otherwise, things stay the same in the state of affairs, so that fluents conflict, but then you have priorities between them. Prioritization tames the conflict and essentially aids modularity. An analogy here would be the gift of fire. So instead of the house burning down from conflict, which is what happens in classical, we have it safely in a stove, for example. Defeasibility is indicated that we ought to have it as a feature and use it when both useful generalities and potential exceptions coexist, so that you can specify knowledge in the detail or precision that's appropriate for various circumstances. It's indicated also when governing doctrine or definitions or other knowledge cannot be assured to be conflict-free, say because there are multiple sources of governing doctrine without a central authority, and because of context dependence, and specification of context. Many broad realms are full of exceptions, so policies, regulations, and laws, and the workflows they drive, learning and science, updating and debate, causal processes, natural language. Peter Clark, who's very senior at Allen Institute for AI, when he was my colleague at the predecessor, he had a great line. He said, the thing about natural language is there's a gazillion special cases. And that's part of the reason why these language models, the LLMs, have to be so large right now. Argumentation rules approach for defaults in LP. As I mentioned earlier, it's the meta rules specify when rules ought to be defeated, and that was a major advance in several regards in practical defeasibility, simpler to implement, faster when updating, more flexible specification of edge case behaviors, and much simpler to analyze theoretically and give strong analytical guarantees, including about proof procedures. And this combines well with other key LP features, extensions in the KR, and has a state-of-the-art implementation. So there are a number of other aspects to meta that we're going to wind up very shortly here, where the big one is uncertainty, and there are a lot of different flavors of it: Bayesian probabilistic, point valued, intervals, other kinds like second order distributions, fuzzy a la triangular norms. We have different choices of the norms that correspond roughly to an assumption about correlation when you're ANDing or ORing. Other kinds that don't fit so neatly into either of those groups, like discretized ordinal or weighted or lattice-based. You can map logic syntax to text syntax and vice versa using the logic itself. And that is a very useful technique when automatically generating explanations, because you can take justifications in the form of a directed graph that fall out of these extended logic program KRs because of their natural deduction style of proof theory, and present that as an expandable tree where the nodes in the tree are presented in natural language automatically generated using the logic itself. You can have richer formulas. I didn't have time to go into that, but scolums are part of that. You can have procedural attachments for external querying, for performing external side effectful actions, for events being delivered as an update to a knowledge base. You can have interfaces for import or export of data or knowledge, batch or dynamic, for querying inbound, either one shot or persistently whenever a knowledge base is updated. It reports out its changes and conclusions. Interfaces for procedural attachments, and also for composing KR with ML and other AI or IT functionality, for example, in NLP, planning, vision, robotics, even doing combinatorial stuff, for example, optimization or so-called constraint reasoning. And so that might be, for example, via Python bridge, as in the Janus component and open source that I mentioned earlier in the practical tools section. There are a number of other kinds of features that are useful in KRRs and mostly could be thought of as meta from some viewpoint as compared to the basic KR, such as integrity constraints, especially as alarms, object orientation, ontologies, and optimization, various other things. So induction can be viewed as deduction in meta logic. And for example, that was the basis for the inductive logic programming approach, whose successor is meta-interpretive learning that uses higher order. And what's going on also in some of the newer systems that have probabilistic or fuzzy uncertainty combined with LP, induction is being done via deduction in an extension of LP that has uncertainty. And abduction is pretty much similar to induction. Okay, so that's it. The next couple slides are just a summary of what we covered, but let's go to questions right now.
Okay. So Alex, is there any question that you noticed in the Q&A section?
Yeah, here's one. Are there zoos or repos for KBs as seen in ML model repos with good KBs for various domains such as computer networks, malicious software, or network activity?
I wish the situation were better in that regard for relatively rich KRR. However, there are such zoos for a lot of the simpler kinds of KRR that is used in semantic web. So ontologies, fact sets, etc. Some of them very large scale, and those have been used for benchmarking and testing and validating in the area of semantic web for the last 15, 20 years.
Another one with reference to higher order logics and reification, there would seem to be strong connections to Martin-Löf intuitionistic type theory, which has been well developed in the programming language community and has many practical implementations.
Okay, that's an interesting comment. I mean, there are many aspects I didn't get a chance to talk about. Yes, there is this important relationship, I think, to functional programming. And historically, functional programming people and logic programming people in terms of programming languages were kind of adjacent or neighbors. And that has, and as I mentioned earlier, LP proof theory can be viewed as intuitionistic. Now, type theory is fairly limited in a lot of ways as a KR in some important regards as compared to the aspects of LP that I talked about, or KR that I talked about here, that are practically important. But it would be great if some people in the field would put more attention into exploring the relationships between intuitionistic type theory and functional programming and logic programming, that cluster of stuff.
Okay, one more. If defeasibility is indicated in situations that require context, isn't it always indicated? Trying to think of KRR situations that do not require context.
Well, part of the limitations of a lot of the older techniques in structured information management in computer science is that people are doing their damnedest to try to minimize the importance or necessity of dealing with underspecified context. So that's a lot of the engineering activities in databases, and semantic web is in fact oriented toward trying to make enough stuff explicit that you can get away without such context dependence. But that's really kind of only a fraction of the potential applications that one wants to be able to have.
All right, thank you. Let me just say we will make an attempt to actually answer every single question. If we didn't answer it live, we'll go into the Q&A and give a response. Of course, feel free also to reach out to the speakers. Now, separately after the event, but we will try to get everything. So thank you, Benjamin. So of course, as you can tell, there are mountains more he could have said. He did a curation of really decades of work. So thank you, Benjamin. Now,
Thanks, Alex.
So,
yeah.
Alex, let me restart recording.
Oh.
Okay, I stopped sharing.
Thank you.
Okay.
Just a second, Alex.
Oh, oops.
It's it's taking some time to stop recording. I don't know what's